All right, here is our how to solve all of the questions on the Lesson 7 DC Theory 5 worksheet that we didn't have time to go over in class. I'm not going to put the questions up on the board. I think you on the screens. I think you guys should have your worksheets in front of you to follow along easily, or hopefully easily. I'll go ahead and read the questions, and I'm going to go ahead and just draw up on my draw pad how to solve. So number one says you have been called to troubleshoot a water heater that is not working properly. It is rated to operate at 3,500 watts, 240 volts, but you measure only 120 volts. How much wattage is being consumed at this lower voltage? So we need to approach this question and just write down what we know. And what I'm going to do are one of our double-sided peer charts. All right, and we're going to have our rated. Because again, keeping in mind that the only thing that the manufacturer can provide us is a resistance. If we apply 240 volts to this heating element, the manufacturer says, because I give you this much resistance, if you apply this much voltage, you'll have this much current flow and you'll have this much power consumed. But we don't have that. We have less voltage. So we have our rated and we have what we actually got. So we are rated at 3,500 and at 240 volts. And again, I told you the only thing that we are guaranteed is our resistance. We know also that we have 120 volts. Now, if you remember from your Ohm's Law, Watt's Law tables, you can kind of skip the steps. So if you're one of my math nerds or if you're one of the guys that remembers your Ohm's Law, Watt's Law, I'm going to do that one real quick first. That is E squared over P equals R. So if you plug in your E squared equals P, E squared over P, you get 240 volts divided by 3,500 watts. 240 volts squared divided by 3,500 watts. And you get 16.457 ohms, which is what you'll have over here, 16.457. It goes out a little bit further, but that's all I'm writing down. And then to get P, you can actually swap over the P and the R over here, and you get E squared over R equals P. So I can now take my 120 squared and divide that by second answer, and I should get 875. Now, if you don't know, memorize, whatever those, we can go ahead and go back to our good old-fashioned, tried and true peer chart. I have 3,500 watts at 240 volts. I divide down, I get 14.583 repeating. I leave that in the calculator. I hit 240 divided by second answer, and I get that 16.457 one that I was talking about before, which is going to transfer over here. I'm going to leave it in the calculator to get more accurate of a response. Again, peer charting, 120 divided by second answer means now I've got 7.29, 1/6 repeating, amps. And I know that I got 120 volts. That was given to me in the question. So I'm going to leave that value in the calculator, 7.2916 repeating, and I'm going to multiply that by 120 volts. And boom, I get my 750 watts of power consumed. Okay. So that's how I can do number one. Either of those two ways. And again, if you want to make sure you don't screw it up, don't use these two formulas. Just go ahead and peer chart it. So moving on to number two. Number two says, what would be the net result of power caused by reducing the voltage applied to a load by 1/2? So I'm just going to go ahead, since that's exactly what happened in question one, I'm going to go ahead and leave question one up here for a sample. So we cut the voltage in half. So our actual voltage is 1/2 what our rated voltage was supposed to be. And as we know, the manufacturer gave us a certain amount of resistance. So if we look at our current flows, we can see that our current flows changed also. So if I take my 14.583, actually I'll take my 7.2916, 7.2916, and I divide that by my 14.583 and hit equal, I will see that that is also 1/2. And that makes sense, right? If I have the same resistance and I cut my voltage in half, I'm going to also cut my current in half. So I cut my voltage in half and I cut my current in half. So if I take those two blue numbers, 1/2, and I multiply them together, 1/2 times 1/2, that is going to give me 1/4. So that means that my actual power consumed is 1/4 of what it is rated. So I bet you if we take 3,500 watts and divide it by 875 watts and hit equal, we'll get a value of 4. Or we could take our 875 watts, divide it by 3,500 watts, and that would give us 1/4. Good. That is 1 and 2. Number 3. You're installing low voltage lighting that operates at 12 volts plus or minus 1 volt and draws 0.4 amps or 4/10 of an amp. If the power source is located 500 feet away, what would be the smallest wire in circular mill? So this question, we're technically not asking for a wire size. We're saying what's the smallest circular mill area we can use. Obviously, once we get the answer, we can go to Chapter 9, Table 8 and find the answer, and we'll talk about it when we get there. So on this one here, I am going to use the formula VA equals 2 kil. And we are looking for a wire size, so I'm going to get rid of the A over here. But wait, no, I'm looking for wire size. I apologize. We're looking for wire size. We're going to bring the V over here. So we have 2. We have a K value, which was given at 12.6. We have a current value, which was given of 0.4 amps. And we have a length of 500 feet. Now, where this question gets a little bit dicey, it tells us that the manufacturer has given us a plus or minus 1 volt. Normally, I would take my 12 volts and multiply it by 3% and see that I could drop 0.36. I could only drop 0.36 volts by the code recommendation. But the manufacturer says I can actually drop 1 full volt. So this will work as low as 11 volts. So since the manufacturer told me that I can drop 1 full volt, that is going to be my maximum voltage drop. It says it right there in the question. Now this is a simple matter of plugging numbers into the calculator. So if we go, and I'll bring this one up on the calculator here, which I probably should have done on the last question. So 2 times 12.6 times 0.4 times 500 feet divided by 1. I don't have to do anything with that. I get 5,040 circular mil. 5,040 circular mil is not a wire size, obviously. If we go to Chapter 9, Table 8, we will see that 4,110 circular mil is a number 14. 6,530 circular mil is a number 12. So if that were asking for an actual wire size, we would have to use a number 12. Okay. And that is number 3. Again, that was tricky because they told us that voltage drop was allowed to be up to 1 volt. It was more than the actual 3% that the code recommends. Okay. Moving on to question number 4 on your worksheet. How many 1.5 volt amp and a quarter 1.25 amp hour batteries would be needed to power a load that requires 9 volts and 2 amp hours? And how would you connect them? Okay. So we have 2 different things going on here. We know that voltage is the same in parallel, and we know that current is the same in series. So first thing I'm going to do is I'm going to figure out how many volts, how do I get to my 9 volts? So I'm going to take that 9 volts and I'm going to divide it by the 1.5 volt battery. So 9 volts divided by the 1.5 volt battery is going to give me 6 batteries. So I'm going to take my 6 batteries and hook them up in series. So 1, 2, 3, 4, 5, 6 batteries. They're all 1.5 volts. Oops, poop. So with all my 1.5 volt, my 6 1.5 volt batteries, that means I've got 9 volts. But we also know that these are amp and a quarter, or 1.25 amp hour. Amps, 1.25. And I'm not going to draw them out. We know that amperage is the same in series. So what I have when I hook up these 6 batteries is I've got 9 volts that is good for 1.25 amp hours. But going back to the question, it says I have a 2 amp hour load. We know that if I parallel another 12 volt source with this, the amperages will add together. So I've got to throw those same 6 batteries in here. I'm just going to draw one big rectangle now. And that'll be 1, 2, 3, 4. There's my 6 batteries that I'm going to hook up that now equal 9 volts at another 1.25 amp hours. And when I hook these together, so this 9 volt voltage source and this 9 volt voltage source, it's each good for 1.25 amp hours, and I plug those together, because my 2 voltages are in parallel, they're going to be the same. I now have a 9 volt, and since my currents are in parallel, they add together. I now have a 9 volt, 2.5 amp hour source. So to answer this question, I need 12 batteries. Six of them each to give me 9 volts and an amp and 1.25 amp hours. Awesome sauce. All right, moving on to question 5. How much would it cost to run a 125 volt half horsepower fan for a day if power costs 6.25 cents per kilowatt hour? All right, so since I was given my cost in kilowatt hour, I want to figure out how many kilowatts this thing runs to begin with. So we know that our power is half a horsepower. So we're going to punch up our calculator again. And we know that 1 horsepower equals 746 watts, or at least I hope we do. So 746 times 0.5 is going to give us 373 watts. I want to get this in kilowatts, so I'm going to divide that value by 1,000, and that is going to give me 0.373 kilowatts. All right, so I have 0.373 kilowatts is what this thing is running. Okay. What my cost is, my cost is 6.5 cents, or 0.06. There's 6 cents, so there's 6.5 cents. 6.5 cents per kilowatt hour. So I'll put a dollar sign there. Per kilowatt hour. And I know, hopefully I know anyway, that there are 24 hours in a day. Because that's what it's asking me. The question is asking me, how much will it cost per day to run this thing? So when I look at this, I can cancel out my kilowatts. Those kilowatts and those kilowatts cancel. Those hours and those hours cancel. And now I'm left with dollars per day. That's exactly what I'm looking for. So, going back to trusty calculator, I have that 0.373 in there still. I'm going to multiply that by 0.065. and I'm going to multiply that by 24 hours, and that means that this is going to cost me 58 cents a day. Per day. And that's as simple as that gets. Again, it's only a half horsepower motor. So. Okay. And now last but not least, and again, obviously you guys have this in video form now, so you can rewind this, and even if it's just to hear my voice and help you put to sleep. It works in class, I know. The last question is actually probably the easiest one on the whole thing. It's asking you for a signal from a transducer varies from 4 to 20 milliamps with a 1 to 5 volt supply. And if you're seeing 16 milliamps from the transducer, what is the input voltage signal? We're going to be doing a lot more complex ones of these next year in instrumentation, but this is truly a directly proportional setup question. I can do it either way I want to. I know that my scale is 4 to 20 milliamps, so 4 to 20 milliamps is also going to be on my 1 to 5 volt scale. So this is milliamp, and this is volts. It's directly proportional, man, however you want to do it. If 4 milliamps equal 1 volt, then what does 16 milliamps equal? Or I can do it on the other side of the spectrum. If 20 milliamps equals 5 volts, what does 16 milliamps equal? And I will go ahead and do both of them. Let me erase this, and I'll punch up the calculator, and I will show you guys that this is directly proportional either way we go as soon as I find my cursor. So I can do 16 times 1 divided by 4, cross multiplying, and that gives me 4. Or I can do 16 times 5. Oops, that didn't clear. I can do 16 times 5 and divide it by 20 for the bottom one. And I get 4. So if I have got 16 milliamps, my output on that would be 4 volts. So this is 4 volts, or this is 4 volts. So they are directly proportional.